Okay, so here we have the problem that I've designed for my H6, which is based on torsional elasticity. So essentially, there's this object that is fixed on the x equals 0 face and has a force applied at the end of this y extension here. And we're going to find the moment that this force produces on the square cross-section of the end of this x extension, the shear stress distribution caused by this twisting moment, and the angle that the centroid at the end of the x extension twists through, as well as the z displacement of the y equals 120 millimeter face, so this end, using Maple and Flex PDE. Okay, so how I solved for this in Maple is first I laid out the material properties and some dimensions here. I have the applied force assigned to a variable, the shear modulus calculated, the cross-sectional width defined, as well as y bar and z bar, which are just half the cross-sectional length. Then we have the moment, which I took as the negative of the applied force times the distance from the end of the y extension where the force is applied to the centroid. And I took this to be negative because if you cross the force applied with the distance along the y extension, this produces a clockwise rotational moment around the x-axis, and the resulting vector points in the negative x direction. Then after this, we have the radius from the centroid, which is y minus y bar squared plus z minus z bar squared. Then we have the shear stresses on x and y and on x and z calculated as the moment over the integral of the area times the distance from the middle with both of them. And then we even have a moment check here, which takes the double integral of these values. Then we have the torsional constant, which is for a square cross section, which is found from the formula in the notes. And then we have the angle that the end of the x extension twists through, which is the length to the centroid at the end of the x extension times the moment over the torsional constant times the shear modulus. And we have the z displacement due to shear at the end of the y extension, which is given by this formula. And then I calculated the total z displacement of the end of the y extension based on the z displacement due to shear plus the angle that the end of the x extension twists through times the distance from the y face to the centroid. And we can see the results below. Okay, now the Flex PDE implementation was pretty straightforward. We have the material properties, and we have the implementation of the angle calculation, which I believe could be wrong, and I've elaborated on why I believe this in the reflection in the write-up. But then we have our matrix methods for calculating the stresses and strains, and then we have our boundary conditions. So on the z equals 0 face, there's no stresses, as well as the z equals a face has no stresses on it. And then we have nothing on all of the faces until we get down to the basically the end of the y extension, and I defined the force the stress in the negative z direction as the negative of the force over the total area of the end of that y extension there. And then we have our implementation of the reporting of the angle and the z displacement of the end of that y extension. And here we have the Flex PDE output. So as we can see, the behavior seems correct. There is a negative z displacement caused by this force at the end of the y extension, and this produces some sort of rotation at the centroid at the end of the x extension. But these results differ from my Maple calculation, so I've elaborated on that in the reflection of my write-up, but I believe it could be a result of improperly implementing the calculation for the angle, as well as the fact that the Maple calculation did not account for bending in the y extension. It assumed it was rigid, so that's why I believe these results could differ.